Hello students, good morning to all of you. Let's learn today one of the very important aspects about differential equation, especially the part of higher order differential equations, where we initiated in the beginning lecture as the topic of higher order ordinary differential equation. Today we are going to learn something about classical method for finding the particular integral. Everybody knows that every higher order differential equation has a solution which is contributing with the two parts, basically the complementary function and the particular integral, where this complementary function part is constituted by the number of constants those are involved in the process of solving the differential equation, whereas the part of particular integral is the actual integration of the right hand side function that we get in any differential equation. If I add this complementary function to this particular integral, the total solution is called as complete solution of a given differential equation. There are various methods which are available to solve the higher order differential equation. Basically, today's lecture is to concentrate on the higher order differential equation, the solution by traditional method of integration, which is in turn or otherwise called as classical method of integration. Let's learn about this method, where I am going to focus obviously more on finding the particular integral. Now, how does it happen and how do we generate the formula which is used for solving a particular differential equation? Let us come into this particular flow. Everybody knows that a differential equation, rather the part of particular integral, is written as 1 upon function of d which is operated on the right hand side function x, where this f of d is nothing but the number of derivatives those are involved in the equation, which is constituted or written in symbolic form as f of d, and the dependent variable here is y, which is operated, where d is operated on y, and we have the right hand side as capital X function, where this capital X is any function of x. Any function of x. When I say any function of x, this gives me the advantage of this particular method over some other methods like solution by standard results. How do we understand this? This capital X, if it is equal to e raised to ax, or it is equal to cos ax, or it is equal to sin ax, or it is equal to something like x raised to m, or it is equal to like e raised to ax into some other function like cos or sine, or maybe x raised to m kind of function. These all type of functions come under the category of standard function, where a ready-made result, a formula is ready for deriving this answer, which is particular integral. We have already studied this part. If you remember, there are standard results, standard formulas available to derive or to find a particular integral for standard list of functions. Now, what is speciality of this particular method, classical method? While finding pi, this capital X function need not be ever a standard type of function. It could be standard or it could be any other non-standard. Non-standard means there is no standard formula which is used to derive the answer as pi. Such functions we call as non-standard function. Apart from this list of function which we talked now, which other functions we can talk about is, if I list out some other type of function where x could be log x function, x could be some hyperbolic function, x could be a combination of these two functions, or x could be anything in terms of inverse algebraic functions, 1 by x, 1 by x square, or anything of this kind, which is a non-standard kind of function. Any such list of function which we have available for x while solving a particular differential equation cannot be solved by a standard formula or a standard result. for such functions we need to focus definitely on something else, and this method comes for our help, which is classical method. This is the advantage of classical method over the other methods which are called as standard results. I hope you understand this. Because of it is a classical method, we can have any kind of function x and we can find pi. So how it happens? Let's understand. If I take an example for this f of d as a equation in terms of d, where everybody knows the concept that d stands for the derivative d by dx. If my equation is, for example, d2y by dx square plus 5 dy by dx plus 6y is equal to, say, I have some function e raised to 2x. I hope you understand here. If this is the differential equation to be solved by using classical method. Now how do we go for this? My focus is very much on finding pi right now. If I focus on that, let's use this capital D as d by dx. This equation gets converted to the terms of capital D. And how does it appear now? This is d square plus 5 into d plus 6. I know everywhere y is remaining, d square y, 5 dy, 6y, let's take that y common, is equal to e raised to 2x. This is our short form of the equation, and we can read it very conveniently as d square plus 5d plus 6 into y equal to e raised to 2x. If I don't go in the details of auxiliary equation and finding the complementary function, I would directly start finding here pi, where I am focusing on the classical method. To understand this, I have this formula ready here. Pi is 1 upon f of d operated on x. Let me write pi as 1 upon, what is f of d for this particular equation or this particular problem? Naturally it is d square plus 5d plus 6, which is to be operated on capital X on RHS, which is here e raised to 2x. I hope you understand this. If this is clear, can I factorize this denominator d square plus 5d plus 6 as d plus 2 and d plus 3 linear factors? If I factorize this way, what is the use of this factorization? You know that pi is nothing but part of the solution. Part of the solution is itself a solution because it is a linear combination of CF and pi which constitutes the final solution. So let us name part of the solution also as a solution. So I am renaming pi as y here. Let me write this way if you are understanding this part. If this is clear to you, if I go reverse way, I am having two linear operators to be operated on this particular function, that is e raised to 2x. How do we do this? To do this particular thing, what do we do is, we take one by one operation on this function, that is e raised to 2x. For example, if I am first operating d plus 3 on this e raised to 2x, what is meaning of 1 upon d plus 3? If d is the operator in numerator which stands for the derivative d by dx, the significance of 1 upon d is integral of that particular function. Numerator d stands for derivative, whereas 1 upon d stands for integration. If this concept is clear, then 1 upon d plus 3 is also an integral which is getting operated on the function e raised to 2x. Now how do we operate these two things? There are many other ways also. I can go by operating one by one. I cannot do two integrals at a time. This is one integral, this is second integral. Let us operate one of these integral first. Say I am operating d plus 3 on this function e raised to 2x. I will solve this part of the question separately. And whatever answer of that particular integral I get, that becomes my new capital X function on which I am supposed to operate the second integral, which is 1 upon d plus 2. I hope you understand this. Let us solve this part separately. If I write this as 1 upon d plus 3 operated on e raised to 2x, y is equal to, can I take back this d plus 3 cross multiplied with y and constitute one or frame one linear differential equation? Is it not linear? As you know, d is linear, degree of d is 1, that means it must be a first order first degree differential equation. And is it linear or not? If you see, d means d by dx, as you already said. This gives me dy by dx plus 3y is equal to e raised to 2x. Can you compare this particular equation with the structure dy by dx plus py is equal to q? What are the conditions for an equation to be said as linear equation? Let us recall. This is the result we have already learnt in first order first degree differential equation. If you want to do this dependent variable y and its derivative, this y is dependent variable and dy by dx is its derivative, both should be coming singly, that means coming only once in the equation. First condition to say the equation is linear. If dependent variable y and its derivative are coming only once in the equation, and there is one more condition to support the linearity, and what is that? This term p and the term q need to be function of x or they are constants. Rather, we can say generally p and q are functions of independent variable or else they are constants. Either of the conditions, I mean they are functions of the independent variable or else they are constants. Two conditions. The first condition on dependent variable, the second condition is on p and q. If these are satisfied, we call the equation to be a linear differential equation. Now, can I say this equation is a linear differential equation? But obvious, yes, it is a linear differential equation. How? Can you see this py is comparable with 3y, where p is 3 means a constant, whereas this q is e raised to 2x, which is another function of x, means p and q are functions of x or constant, and the dependent variable y and its derivative are coming only once in the equation. Can I say because of this is a linear equation? Now, how do we solve linear equation? If you recall, to solve the linear equation, we need to find integrating factor. We convert linear equation to rather an exact equation by using that integrating factor. What is the formula for the integrating factor? It is e raised to integral p dx. What is the value of p here? P is 3 and q is e raised to 2x. If I use this, I get the integrating factor as e raised to integral 3 times dx. Is it not equal to e raised to 3x? If integrating factor is e raised to 3x, I can write the solution for this equation. What is the solution given by? Dependent variable y into integrating factor, y into if, y into e raised to 3x, agreed by all, is equal to integral q. What is the value of q, or what is the function q here? E raised to 2x into again integrating factor. What is the integrating factor? It is e raised to 3x, which we got just now, multiplied by dx plus the constant c, which comes in the solution. But I won't write any plus c here for the reason we know that we are solving not a first order equation, but we are solving right now the second order differential equation, where the constants are already taken care in the function part, that is complementary function. So, I am not adding any c anymore here, allow me for that. I hope you are agreed with the all constants whatever are there are already there in contributing in complementary function. So, look back to this one where there is no c to be added here in the formula. This gives me e raised to the addition of index, and what is the integral? It is e raised to 5x divided by 5. What is it all equal to? It is y e raised to 3x equal to e raised to 5x upon 5. What is happening here? Can I say this is y equal to, can I divide this e raised to 3x on this side? It will give me e raised to minus 3x. And what is the answer that I am getting? E raised to 5x divided by 5. This will give me the answer as e raised to 2x divided by 5. But what is that hidden formula behind? Can you work out that now? If the factor is 1 upon d plus a, is it not parallel to d plus 3? I am generalizing the result now for you. If y is 1 upon d plus a and the general function if I read as capital X as usual as we read here, what is the formula? The formula becomes, can you see, if it is d plus 3, I am getting e raised to minus 3x outside. That means if it is d plus a, I should get e raised to minus ax outside. Correct or not? Into, what is the integral remaining with multiplication with it? Which is, if I see here particularly, what is the power of e in this term for integrating factor? Positive 3x. If d plus a is there, what goes inside is e raised to ax. Agreed? D plus a, if that is the factor, linear factor, to be operated on x, I get e raised to minus ax into integral e raised to ax multiplied by the capital X function, whatever it may be. For this example, it was e raised to 2x. For another example, it may be log x, cos x, tan x, whatever. If I am talking about this result, this becomes a formula which can be used for the classical result. Now, what is the change or what kind of factors we can get more than this? If I am having d plus a generated, can I generate d minus a also? How do I generate the result of d minus a? Just replace positive a by negative a. Let us write the result. What will be the result for pi if the factor is d minus a? If y is 1 upon d minus a operated on x, the result would be, can you compare and parallelly say with this? If it is plus a, we get minus ax outside. That means, if it is minus a, I should get positive e raised to ax outside multiplied by the integral, which will be e raised to negative ax into capital X into dx. This gives me the formula for the factor which is of the nature d minus a. Real factors, if you are getting for a quadratic equation or for any kind of polynomial in terms of d that you get, then the result is going to be always in two ways. Either it is d plus a or it is d minus a. This gives you a very well set definition to find out the result, that is particular integral. Can I complete this problem using this formula? I already got one of the results. The first answer for pi that you are getting is e raised to 2x upon 5. Now, where I am going to substitute this e raised to 2x upon 5 is this particular part, where one more operator is still there, which is 1 upon d plus 2. And what is that new capital X that you are getting? That is this answer replaced by e raised to 2x upon 5. Let us complete this. If I want to complete this ahead, I will rub this part and write here the next part where y is 1 upon d plus 2 to be operated on. What is the result I am substituting for the square? It is e raised to 2x divided by 5. Let us simplify this now. Again I have d plus a kind of factor here where a is 2, result is available. Can I use this as e raised to minus 2x integral e raised to 2x multiplied by e raised to 2x divided by 5 multiplied by dx, that is in this factor multiplied by capital X, where capital X is this function. This gives me e raised to minus 2x into, it is integral e raised to 4x divided by 5, multiplication of two terms. And what is that answer? E raised to minus 2x into e raised to 4x divided by, is it not 5 into 4, which gives you 20? And the final answer for pi would be e raised to 4x minus 2x. The addition of index gives us e raised to 2x divided by 20. This constitutes your solution. If you write this solution as complete solution, which is CF plus PI, where we solve this PI part for this particular function. What is that equation we studied here? The solution of d square plus 5d plus 6 operated on y equal to e raised to 2x. I hope you understood this. So what are the two results? Can we conclude the classical method with these two results? Let us write these two results and make this sure that we can apply it for any such function which is non-standard one and find the answer for the particular integral. I am summing up with this method, writing these two results and generalizing it for any kind of capital X function. Let me write f of d operated on y is equal to x, then pi is given by, if the factors of f of d are d plus a operated on x, then what is the answer? We get the answer as e raised to minus ax integral e raised to ax into capital X into dx. Whereas if I get the factor as 1 upon d minus a to be operated on x, I get the answer as e raised to ax into e raised to minus ax into capital X into dx. Can you remember this story to solve any function which is a non-standard one? To summarize, let's take a simple example and solve this and make this method very sure one for you. Suppose I have the equation as, I'll write directly in D form, directly capital D form. I'll start on this side writing it as d square plus 4d plus 4 into y is equal to e raised to x. The auxiliary equation would be d square plus 4d plus 4 is equal to 0. As it is auxiliary, we are equating it to 0. It's a dummy equation giving me the roots or the values of d. What are the values of d? It is d plus 2 whole square equal to 0, giving me d as minus 2 and again minus 2 repeated twice because it's square of the bracket. Agreed? So how do we write the complementary function in case of real and repeated root? If you remember, it is c1x plus c2 multiplied by e raised to minus 2x. Ahead, if I go ahead with this, the particular integral will be 1 upon d plus 2 into again d plus 2 operated on e raised to x. How do we conclude here? Let us operate this 1 of the d plus 2 on e raised to x, keeping one d plus 2 reserved. One is on reserve, another is getting operated. This d plus 2 is parallel to this d plus a. This gives me e raised to minus 2x integral e raised to 2x multiplied by e raised to x into dx. Capital X is e raised to x. If I go ahead, it is 1 upon d plus 2 e raised to minus 2x into, let us solve by substitution this integral. Can I put for this e raised to x as t, which gives me the derivative as e raised to x into dx as dt. If I substitute here, it is e raised to 2x into e raised to t, and this e raised to x is t, substituted as t, so e raised to 2x can be divided as t into, this is e raised to t, and one of the e raised to x into dx can be substituted as dt. What is the answer for this integral? It's a famous integral, t e raised to t. We have integrated number of times this integral. The answer for this integral comes as 1 upon d plus 2 as it is, e raised to minus 2x as it is, The answer for this is e raised to t into bracket t minus 1. This is the integral by parts, where exponential function becomes the second function and t becomes the first function. First into integral of second minus integral derivative of first into integral of second, and that e raised to t, if I take common, this is my answer. But what is t? Going back to t, where t is again e raised to x. So what is that function I am getting? I am getting the function as pi is equal to 1 upon d plus 2 into e raised to minus 2x into e raised to x into e raised to x minus 1. Do you agree? And this gives me further 1 upon d plus 2 e raised to x. Let's multiply this e raised to minus 2x inside, which is going to give me e raised to minus x and minus e raised to minus 2x. To simplify this, I will operate d plus 2 again, which is e raised to minus 2x integral of e raised to 2x into the function capital X, which is this whole one, e raised to x e raised to minus x into e raised to minus 2x into dx. This gives e raised to minus 2x integral e raised to x. I am multiplying this e raised to 2x inside, which is going to give me e raised to x minus this e raised to 2x into e raised to minus 2x gives you e raised to 0, which is 1, multiplied by dx. The integral of this particular term can be evaluated by simplifying this integral. And what is the answer? Again you have to substitute for this e raised to x as t, and e raised to x dx becomes equal to dt. Let us solve this one step ahead. This gives me e raised to minus 2x integral. If I put for e raised to x as t, that gives me e raised to t. This e raised to x is t minus 1, and what about dx? That dx is dt upon e raised to x, means dt divided by t. If you simplify this integral further, this is equal to e raised to minus 2x integral e raised to t. If I simplify this as 1, t divided by t becomes 1 minus 1 by t multiplied by dt. If I solve this particular integral by using integration by parts, I will be able to find out the answer for particular integral. And if I add the complementary function to the integral, that is pi, I can constitute the complete solution. So final solution becomes complementary function plus the particular integral. The aim to give you this problem was to revise the results of these two kinds. This is the classical method. 1 upon d plus a operated on x is e raised to minus ax integral e raised to ax into capital X dx. And for 1 upon d minus a operated on x, the result is e raised to ax integral e raised to minus ax into capital X into dx. You might have understood how much the linear differential equation plays a significant role while solving the higher order differential equation. I hope you understood this method. You can solve many more problems on this, and you can discuss the doubts if there are any. Thank you.